Okay, a little summary then of all about shapes and sizes. There's some basic things you have to remember. Every right angle, triangle, has an angle here of 90 degrees. So how many angles are there in a full circle? Well, here we can see in this shape that there are 4 right angles. So the number of degrees in a circle must be 90 degrees, which is 1 right angle, and we have 4 of them, times 4, giving us 360 degrees. There are 360 degrees in a full circle. And we have some different names of these angles that are important to remember. An angle that is less than 90 degrees is called an acute angle in English, and in Swedish it has this name. An obtuse angle is an angle that has an angle of greater than 90 degrees, and in Swedish that is called, yeah, that's right, this. And then we have a right angle triangle. We have a couple of different names for or a right angle here. We can also call this angle a perpendicular angle. Perpendicular means where 2 lines meet one another and the point that they meet is right angled. Okay, so we have 2 different expressions for that. And in Swedish it's called that. Then we have to think about these lines. The one that goes horizontal to the ground, that's the horizontal line. And the one that goes straight up at a 90-degree angle, a perpendicular angle, is the one we call the vertical line. And in Swedish, this one is called that. And this one is called that. Okay, so these are basic terms you need to know for this chapter and need to remember. And you have to remember how to measure your angles with your protractors. Okay, so what other basic facts do we need for this chapter? Well, we need to know that all of the angles on a straight line, if we start here with this sketch, all of the angles on a straight line are going to be half of a full circle, which is 360 divided by 2. So all of the angles on a straight line are going to add up to be 180. So if I have an angle here that's 80 and one that's 70, x plus 80 plus 70 must all equal 180 degrees. 80 and 70 is 150. So the angle that's left over here, x, must be 30. Because 30 plus 150 equals 180. So x equals 30 degrees. But we also know that all the angles in a triangle add up to be 180 degrees. So by the same mechanism, 70 plus 80 plus x equals 180. Why do we know this? Well, I don't know if you remember, but there was an activity where we actually cut all of the angles of the triangle here. And then put them together, moved these angles, and stuck them together on a straight line, and proved to ourselves that every single angle of a triangle, because nobody in the class draws identical triangles, always add up. If you put the angles of the 3 angles of a triangle, they will always add up to be 180. So by the same mechanism here, exactly the same technique, we'd get 150 degrees plus x equals 180 degrees. So x must equal 180 minus 150 equals 30 degrees. Then we had some things that we had to remember about equilateral triangles. And an equilateral triangle is when all of the angles are the same, which means they've all got to be 60 degrees, because if they're all going to be the same, they've got to be 180 divided by 3 equals 60 degrees. When the angles of a triangle are all identical, the lengths of the sides are all identical. So we had a few problem-solving questions. This is one of them that I've taken as an example. That this is a flagpole, okay, Swedish flag up here. And somebody has measured that the angle at 12 o'clock in the day from the flagpole to the end of the shadow is 6 meters. The length of the shadow is 6 meters long. And they've also told you that it's the middle of the day, so the angle between the shadow and the top of the flagpole, the very, very top, is 60 degrees. Well, what you have to do here is sort of sketch back and do a reflection of this triangle here. So let's try and do that. Imagine that we made a big triangle out of this. If this angle here is 60 degrees, this imaginary angle here is also 60 degrees. If I've done a complete reflection, I've just copied from one side of my flagpole to the other, which would mean that this angle here would also be 60 degrees. And if half of this triangle is 6 meters, then the other half of this imaginary triangle is also 6 meters, giving me that not centimeters there, 6 meters, giving me that the whole length of this triangle, I've done it again, the whole length of this triangle is actually 12 meters. Okay? Well, if the length of this is 12 meters, then the length of this is 12 meters too. So we've got 12 meters and 12 meters and 6 meters. And then we can use that to get the height of the flagpole as well. The way they wanted you to solve this, because you can solve this quite easily when you get up in 9th grade. There's a theory called Pythagoras theory that will teach you exactly how to work out the length. But the way that you were supposed to work out the length of this triangle, or the height of the flagpole, sorry, was actually just to measure in your books. It was to draw a 6 centimeter shadow and put in a 60-degree angle and then work out how high the flagpole would be. And when you get older, there's quite an easy mechanism for actually working out, using your math skills, that height. But you didn't need to do that for that question. Okay, another thing that we did, and this was probably one of the most complicated things that we did in this chapter, was measuring the internal and external angles of a polygon. Do you remember that? If this was a regular pentagon, where all of these lengths on the external here were the same length, and we know that we've got 360 degrees is all of the inside of the circle here. So the angle of x must be 360 divided by 5, which would be 5s into 36, 7, 1 left over, 5s into 10, 2, 72 degrees. So each of these angles in here is 72 degrees. But each of the angles within the triangle, here and here, are the same length. So these two lengths, although they don't look like that in my sketch, they're supposed to be exactly the same length, meaning that angle y is the same as this angle y in the other end of my triangle. So I know that y plus the 72 degrees that I've worked out that x equals must equal 180. Which allows me to work out what y equals. I would get that 2y plus 72 equals 180. So 2y equals 180 minus 72, which would give me 108. 108 plus 72 is 180. So 2 times y equals 108 degrees. And if I look here, I have a y on this side of my triangle and a y on this side of my triangle. So I actually do want to know what 2y equals. So all of these internal angles of the polygon here, if they weren't triangles there, each of these will be 108. This angle here would be 108. this angle here would be 108. And the same thing here. So the angles of my pentagon, if I was to work out all of these external angles and imagine that there was no triangles there at all, and I wanted to know how many angles can I expect in a pentagon, I would expect 108 times 1, 2, 3, 4, 5, 5. Giving me that all the angles of a pentagon would be 5 8s 40, 5 zeros are 0 plus 4, and 5 5s 540. So all the angles of a pentagon would add up to be 540 degrees. The only other thing I think you need to remember from the chapter is, of course, all your basic skills of remembering how to work out a perimeter and area of a square, that you've got the length times the breadth. Area equals length times breadth. Perimeter equals 2 multiplied by length plus breadth. Try and remember this factor term here, that we've got a 2 in the front, and if we add L and B here together, L plus B, we'll know what half of our rectangle is. So L plus B times 2 will give us our whole rectangle. But we've also got to remember how to be able to work out areas and perimeters for triangles. And the tricky thing here was remembering that the area of a triangle is the length of the base of the triangle multiplied by the perpendicular height. The height that connects this point up here to this line, even though we make it imaginary, at a 90-degree angle. So if we were going to calculate the area here, we wouldn't measure the length of this whole line, because this imaginary angle doesn't get counted in at all. If we're going to calculate the area of this triangle, we use the base of 3 centimeters, and we multiply it by the perpendicular height, 5, and then we divide all of that answer by 2. Why divide it by 2? Because this isn't a rectangle, this is a triangle, which you can consider to be half of a rectangle divided by 2. So we get 15 over 2, which equals 7.5. The most common mistake, centimeter squared, units of area. The most common mistake that I see is you calculate the area correctly using the base and the height, and then forget to divide by 2. So please, please, please remember, if you're calculating areas of triangles, it's always divided by 2. So you weren't able to use this 10 centimeter or this 7 centimeter at all. You wanted the vertical height of 5 centimeters for the area. But you do need these lengths if you're going to work out the perimeter, because the perimeter is just how much piece of string you would need to measure the lengths of the outside of the triangle. So if you were going to calculate the perimeter of this triangle, you would take the base of 3 centimeters plus the first side of your triangle, 7 centimeters, plus the third side of your triangle, 10 centimeters, giving you a perimeter of 20 centimeters. So that's basically the chapter on triangles, areas, perimeters, and being able to work out angles. Quick summary.